All right, we're almost done. Let's briefly review the four sort of primary types of process that we're considering and the sort of modifications that we can make to the first law of thermodynamics for each of those four kinds of process. In an isochoric, same volume process, the volume is constant. If the volume is constant, that means the system cannot do any work. And if the system can't do any work, then the first law of thermodynamics reduces to the fact that the internal energy must be equal to the heat transfer. Okay, isobaric. If isobaric, the pressure is constant, which means that the change in the internal energy, according to the first law, would be Q minus W, but we know what the work is for an isobaric process, so we can write it this way. We can make a slight sort of simplification to the first law there. For an isothermal process, the temperature is constant, which means that the internal energy is constant, which means that the work done is equal to the heat transfer. And for an adiabatic process, the heat transfer is 0. So the first law of thermodynamics reduces to the change in internal energy being equal to the negative of the work done. If the system expands, then the work done is positive. It expands and cools down because the temperature change has to be negative then. So that's sort of the lay of the land, as it were, after chapter 19. Now our job is to talk about how best to build an engine. Which of these four do we want to use? Now, we are not going to get work without any investment of energy. You know, if we can't just create the energy, the ability to do work. The engine has to have this energy to transfer it to its environment as work. So it's got to come from someplace. And I think it has to come from our initial investment, that there has to be some energy transferred into the system. And then our goal, otherwise we're violating, the first law of thermodynamics. We can't get work from nothing. Either if the system's doing work, then there has to be some energy transfer somehow. Some energy transferred in to begin with. So we can't violate, conservation of energy. We can't create energy where there wasn't any, which means our initial investment is part of the story. And I think the question then has to be, how much of our investment can we recoup? What's our return on our investment? If we put in an investment of Q, how much of that investment can we get out of the engine as W? And that makes me think that the isothermal process is the way to go, because the work done by the system is the heat transferred in. That because we're not allowing the temperature to change, all of the energy transferring into the system as heat is being transferred out by doing work on the environment. That's what we want. And that's fantastic. So we just need an isothermal engine, which is a problem. And it's a problem because any thermal system that we want to make an engine out of needs to have a temperature difference. It cannot all exist at the same temperature. It cannot be entirely isothermal. There has to be a one, high temperature and then another low temperature. And the QH is our, you could think of that like our investment. And then QC is like the leftover. It's the part of our investment that we didn't make back. We invested QH, we withdrew W, and we were left with QC that we don't get to use. It's like a transaction fee almost. And the reason there has to be a temperature difference, if TH and TC are the same temperature, then this isn't, we can't get any work out. We can't get any net work out. And here's why. This is a figure we've seen before from chapter 19, but the deal is the system is doing work because pressure. If the pressure during expansion is the same as the pressure during compression, because the temperatures are the same and it's the same cylinder, so it's an equal volume, right? If the volume change from here to here by dx occurs at some pressure, and then we turn it around and the compression from here to here, negative dx, occurs at that same pressure if it occurs at the same temperature, because ideal gas law, same volume, same temperature, got to be the same pressure, then the net work done, we did positive work on the way out, negative work on the way back, we just did a net work of 0. This is an entirely useless engine. It doesn't get us anywhere. I mean, it's like, it's like taking your oars, putting them in the water, and then pushing them away from you, and then pulling them back without lifting them out of the water first. If all you do is just waggle the oars back and forth in the water, your boat just moves back and forth, and you don't actually get anywhere. So that piece where we push down on the oars so that the ends leave the water and we can move them back, that's really important. And that's like analogous to the temperature change that we need, because we need the pressure to be different. If the pressure isn't different, then the work done is 0, and we don't have an engine. We just we've got a boat that moves back and forth. So there has to be a finite temperature difference. So we can't just use isothermal. I think I'd like to use as much isothermal as I can, but now the question is, what's the best cycle to design using these 4 kinds of process? And over the years, we have tried several things. This is a diagram of a traditional internal combustion engine in cylinder, the Otto cycle, named after the inventor. This is a sort of a conceptual picture of what's going on. The intake valve is open in step 1, and we're bringing a fuel mixture into the cylinder. The fuel is brought in by the partial vacuum that's created when the piston is actually expanding due to the rotation of the crankshaft. It's pulling that piston down, which creates a partial vacuum which pulls the fuel mixture in. And on the way back, the compression happens, and then there's an ignition, and that ignition causes a heating and expansion that pushes the connecting rod down, rotating the crankshaft again. And then on its way back up, the piston pushes the spent fuel out through the exhaust valve when that opens, and then we are ready to close the exhaust valve, open the intake valve, and repeat the cycle again. What does it look like on a pressure volume curve so we can calculate the work done? it looks like this. And having said what we did about isothermal processes, this is not a fantastic. It's a first draft, right? It's a first draft at an engine. We've got two isovolumetric processes here, which, if we look at the list, in an isochoric process, the work done is 0. So we're not getting anything from the processes between D and A and B and C. They don't do anything for us. They just allow us to change. They allow us to do thermal engine, right? The transition from B to C, that's our input, QH. We ignite and burn the fuel that we put into the system, that QH, the heat that's released from the combustion, that's our investment. And then the process from D to A is the process by which we take the spent fuel, the burned leftovers, and throw them out of the engine. We just take that thermal energy and push it out into the environment so that we're ready to intake again. The second volume, the larger volume here, is written RV, and that's that parameter R is called the compression ratio. It's the ratio. It's a parameter by which we keep track of how what fractional volume change. We start at a volume V, and then, all right, so then the other operating volume, the largest volume, is what factor of that, what multiple of that original volume. These these constant volume processes bum me out. We don't get any work from that. So we've also tried the diesel cycle, which changes not a lot, actually. We still have an adiabatic expansion power stroke. We still have an adiabatic compression stroke. And we still have cooling at constant volume. Take the exhaust, push it outside without really changing the volume that it takes up. But instead of stopping the adiabatic compression at point B, and then using an isovolumetric, isochoric process to go from B up to the hot temperature C, the diesel cycle allows the adiabatic compression to go all the way up to that same pressure, and then gets us a isobaric process during the initial combustion. So at the same time we are igniting and burning the fuel, we're allowing the cylinder to expand a little bit at the same pressure, and that gets us a little bit of extra work. It's a more efficient engine. And your work in the recitation this week is is about how much better exactly, given an Otto cycle engine operating between two temperatures. How efficient is it on paper anyway? Never mind the fact that the metal that makes up the engine actually does get hot, and that emits thermal energy out into the environment. So that's energy that we don't get back because it doesn't stay in the system. If we ignore those kinds of loss, imagine we made a perfectly insulated engine that could do this. What would the theoretical Otto efficiency be, and what would the theoretical diesel efficiency be? And then the follow-up question: what's the best? Can we do better than the diesel cycle? The answer to that question requires us to examine the processes that we're using in a little bit of a different light. Suppose we have a metal box at 70 degrees Celsius and some ice inside at 0 degrees Celsius. The thermal energy will flow from the box to the ice and the water, and eventually they will reach some thermal equilibrium at some other temperature, let's say 40 degrees Celsius. This never happens backwards. You can never start with the metal, the box on the right. We can't start with a metal box and water at 40 degrees Celsius and then sit there and put it on the table and watch without doing anything as the liquid water cools down and freezes while the metal box heats up. It's not a thing we can do. This process only works in one direction. It's irreversible. We cannot reverse this process. Once the ice is melted, it's been melted, and no amount of sitting and waiting is going to change that. Contrast this process with this process. Suppose we start with a metal box and ice all at 0. If we add a little bit of heat, if we change the temperature of the box by some tiny calculus-sized amount, we can nudge some of the ice into melting without changing its temperature. And then if we just nudge it the other way, if we decrease the temperature of the metal box just negative 0.000001 degrees Celsius, we can induce thermal transfer the other way and refreeze the ice. And we can do that with infinitesimal temperature changes without changing from 0, basically. We can do freezing and thawing and freezing and thawing and freezing and thawing. We cannot do that here. We could change the temperature of the metal box as much as we want. We'd have to change it a finite temperature change in order to refreeze the liquid water. We'd have to make it, I don't know, even if we'd have to make it negative 70 or something in order for this trick to work. But here, we can nudge the system one way and nudge it back the other way, and we don't really need to think of this like a stable equilibrium. We can perturb the system from equilibrium a little bit, and then we can bring it back. This equilibrium, well, I guess this is a more stable equilibrium, the box on the right. This metal box and this liquid water at 40 degrees, if we change the temperature of the metal box by some infinitesimal amount, nothing happens. It's a much stabler equilibrium than this one. This one we can kind of, at least this is as stable a temperature equilibrium, but we can actually push the phase back and forth. We can reverse this process with an infinitesimal temperature change. And that's the key. The small temperature change that we put in to melt the ice, we can get back and refreeze the ice. This is an entirely efficient process, this reversible process. Here, the thermal energy of the metal box, once we've used it to melt the ice and change the temperature of the water, we're done. We can't turn this around. We can't get that energy back. We've converted the thermal energy of the metal box into work to change the crystal structure of the ice and change its phase. And then to change the temperature of the liquid water. We can't undo that. We can't get that thermal energy back. But we can if we conduct all of this at the same temperature. So reversible process is an efficient process, and efficiency is what we're after. All right. By infinitesimally raising or lowering the temperature of the box, we can induce heat flow into the ice or out of the water. At without a temperature difference. Okay. But we just said there has to be a temperature difference in an engine in order for the engine to be able to do anything useful. Sure, we can go back and forth and back and forth, but this is the boat. This is the boat with the oars entirely in the water. We're not actually doing anything. Yes, we can reverse it, right? We can push the oars forward and push them back, and that's fine. But yeah, we can toggle back and forth between water and ice, but there has to be a temperature difference. We just want to make sure that if the temperature changes, that it is without heating. If we can do temperature change without heating, if heat flows through a finite temperature difference, then then that's the thing we can't do. This is a slide that represents heat flowing through a finite temperature difference, and we can't turn that around. Heat, Q, has to occur during an infinitesimal temperature difference, a zero temperature difference, in other words. Okay, so if our Q, our investment, and then our exhaust, whatever exhaust there is, right? If those things have to happen during isothermal processes, then we want heat transfer not to occur during the other processes, because if heat transfer occurs during any process other than an isothermal process like we're talking about here, then it's not as efficient. We cannot reverse it as much. So the other processes, okay, so all right, so hold on. We need an isothermal process because reversible, because heat flow during an isothermal process, like this one, is reversible and therefore efficient. We can recoup our investment. But we also need a kind of process that allows the temperature to change without any heating, without any Q, and that's adiabatic. So now maybe we're thinking that Otto and Diesel weren't too far off. They were thinking about adiabatic expansions. But the other processes need to be isothermal, and that's the piece we need. And that's the piece that Sadi Carnot, a French engineer, realized. And he proposed the Carnot cycle, made of adiabatic expansions and compressions and isothermal expansions and compressions. And note that QH is occurring during step one is an isothermal expansion. The investment into the engine happens during an isothermal process, which means reversible. If no heat is flowing, then we can reverse the adiabatic expansions. That's okay. But the adiabatic expansions allow and compression allow the temperature to change without doing any heating, which would be irreversible. This process, this cycle, the Carnot cycle, we can show that it is more efficient than either the Otto cycle or the diesel cycle. How efficient is it? To answer that question, we need to talk about adiabatic processes a little bit. So I'm going to stop the segment here, and we'll talk about adiabatic processes next.